Thank you for
Oh, I love
coming back.
I definitely.
Part two.
Or if they even.
So part one was done in the airport while I was flying back from a trip, and part two is mostly because of our rehearsal dinner. It was done. My son is getting married next weekend, so our house is in absolute turmoil. So again, I have no slides. I would have loved to have some pictures this time, but I'll tell you kind of where you can Google stuff, and you'll probably find really neat pictures online. So I'm sorry for the lack of slides, but I think it actually will help us to get through what is so crazy in such a short time. So let me pray really first, and real quick first, and we'll get started. Lord, thank you that we can know anything by looking at your creation. Thank you for the game of science that's trying to figure things out by what we can see and study about the creation. And help us to enjoy that game, but not see it as the end all of human existence, or the source of true wisdom, or that we'll even be able to figure everything out. And help us to laugh along with the uncertainties that people have, that very smart people have erred or overlooked things, and help us to stand in awe of the creation that you've made in our universe, and appreciate just how strangely you constructed it, and try to imagine the creative power that it took for this place we're in to exist. Thank you, Lord, for this time together today. In your name. Amen. So last week I talked about flatland, an imaginary universe that exists without any height. It's a plane. It exists in a plane, and there is no such universe as far as we know. But it's a concept that helps us to understand our universe. So with the background from last week, I'll talk a little bit about where flatland and our universe overlap. But I want to walk you through the process that people think is the way our universe came to be as it is today. It's called the standard theory, and that's just because there's lots and lots of various theories, and physicists are trying to come up with one theory they sort of agree on, and what's the gray area? It's almost like scripture. It's almost like, okay, these books are definitely part of scripture, these other books are historical literature. And just like in the church, there's lots of physicists who have very wacky ideas about things that they're still bouncing off people and say, hey, maybe this could be true, but generally doesn't have a lot of agreement in the physics community. But what I'll do is try to stick with the standard theory, and I'll point out some of the detours that people are thinking about. But let's just start right off. I'll also be talking a little bit about how amazingly I think the scriptural revelation of creation really does match very well with cosmogenesis. Cosmogenesis is the forming of the cosmos, the universe, not just the earth, but everything. So first of all, you just think, how audacious is it that people would even try to figure out how the universe came to be? But there are some clues, and overlooking at these clues, people have made huge errors and then fixed them, and made more errors and fixed those, and we're at a point now where I'll end with kind of some question marks that will make you wonder if we really do know much about the universe in the first place. But let's start out with the Big Bang. Everybody heard about the Big Bang. When I heard about the Big Bang, especially when I was teaching at Biola, there was a group of people at Talbot that were very concerned about the Big Bang. And I think it was because of the day-age debate over whether God created the earth in 7 or 6 literal days and rested on the 7th. So, but in general, to me, the creation of the universe in a single moment, a Big Bang, puts the biblical account of creation it's much more aligned with the Bible than it is with various spiritual beliefs where the universe has always been here. Like the universe has always existed, it's just the backdrop on which everything plays out. But in the physics community, the standard theory says that this Big Bang, it was where about 13.8 billion years ago, give or take 200 million years, there was an event, and it's called, the popular word is Big Bang. That was kind of a mocking term for the theory when it first came out. Physics likes to call it a singularity. A singularity in the sense that all of everything in the entire universe, all of the matter, all of the energy, existed at that singularity in a space smaller than an atom. And it just came into being in a huge amount of energy in a tiny, tiny thing smaller than an atom. In fact, it's a singularity. that was apparently the beginning of our universe. That is such an incredible concept to think about. If you think about E equals mc squared, Einstein says energy and matter, so all of us, all of our material stuff, is equivalent to a certain amount of energy, which is equal to the mass times the squared speed of light, which is a number that's huge. So in all of the atomic bomb, the 2 atomic bombs in World War II, plus the Trinity test, plus all of the other atomic bombs that have ever been exploded in testing, less than 5 pounds of material was converted into energy overall. Atomic weapons are really inefficient at converting fissile material like plutonium into destruction or energy for power. So if you can imagine all of the matter in the universe, all of it converted to energy, we can't even imagine it. And yet, if physics is right, at that moment of creation of the universe, it existed in a single point in space. Well, it was space. I'll get to that too. So our universe had a beginning. Everyone seems to believe that. That's the standard theory. It definitely had a beginning about 13.8 million years ago. All the matter existed in that one little tiny spot. So what happened afterward is just the progression of that. What would happen? The physicists ask themselves, okay, what would happen if that much energy was in that small of a spot? Well, it's going to expand, is what the answer is. And it's going to spread out. And so for the creation of the universe we see today is believed, but this is a lot of mathematics and a lot of theory, but here's kind of the timeline, if you bear with me. So the largest changes in our universe happen within the first few seconds after that singularity. And to look at the creative events, there's actually called epochs after the Big Bang, in this time afterwards as it started progressing. They call them epochs, but the first epoch is only 10 to the minus 43 seconds long. So that's point 43 zeros 1 at the end of a second. At the end of that vast period of time, called an epoch, right? Okay, but this is a physics, right? So physics people they're used to thinking about like nonlinear time. You know, it's like you can brush your teeth in 1 minute.
That could be a whole other talk if you want to talk
100
about
minutes to get 1,000 minutes when it's birthday. No, so the idea of this epoch, all in that first 10 to the minus 43 seconds, which has a name, is called 1 Planck. It's like a second. It's named after Max Planck. But it's a time unit in physics for the creative events. Now it's useless for anything else because that's so short of a time that almost nothing happens in it today. But at this point in time, where all the energy of the universe was in that tiny little spot, bam, what happened then? All the forces were equal. All the forces that you heard about, the unified field theory in physics, physicists believe that in that first Planck, 10 to the minus 43 seconds, all the forces were there. The nuclear force, the gravitational force, the electric repulsion that keeps your socks sticking together in the dryer, magnetic forces like moves the compass needle, all of those forces were present and they were equal in power, equal in strength. So those forces had no difference between them. It was just an incredibly bizarre kind of physics. No one's ever seen it. It's just been driven by mathematical models of what would have happened if we believe physics is right, the way we understand the particles today. By 10 to the minus 36 seconds, that's a point with 36 zeros and a 1. That next epoch, they have names, but I didn't want to bother you with the names. In that next epoch, gravity became separate from the other forces. Gravity is a weak force. In physics, we have strong forces and weak forces. The strongest ones are like the electromagnetic force, and the magnetic force is a strong force. Gravity is a weak force, and that has to do with just they're vastly different in the way the mathematics, the same equation, but the numbers in them are much, much smaller for gravity. So in that 10 to the minus 36 seconds, that next epoch, gravity became a thing that's different from everything else. Now, mind you, there's still no matter. There's nothing. It's just energy. But gravity is supposed to have come to exist. 10 to the minus 32 seconds, the nuclear force separates. So that the nuclear force is the thing that holds the positively charged protons together in the nucleus of an atom, which is a mystery in itself. I'm a chemist. We never even studied that stuff because that's physics. I just start where an atom is the atom and the nucleus is there, and we don't mess with the nucleus, right? We just do electrons is all of our body's chemistry. Nucleus is just stuff that we're building on. At that moment when the temperature had reached we're still talking billions of times higher temperature than the surface of the sun. So there's no matter, it's just this amazing ball of energy. At that point, the nucleus could form. And so the nuclear forces started to attract particles together for the first time. And that force it caused the universe to undergo what they call an inflationary epoch. And so the universe went from this tiny little thing to something about the size of a grapefruit.
Oh.
A grapefruit-sized universe. And this was called the inflationary epoch. Now, mind you, this is still 10 to the minus 32 seconds. A lot of stuff happened. 10 to the minus 12 seconds, exotic particles start to form. And you might have heard about the God particle, the Higgs boson. That's a particle that all the other particles can derive from. And so it's kind of like if stem cells are to liver cells, the Higgs boson is like that for all the other bosons that are particles in physics, like neutrons and all those are hadrons. Sorry, I'm talking about there would be quarks and things like that. So the particle zoo, I'm not going to go into, okay, because we'll all go nuts, right? There's quarks and leptons and hadrons and bosons. All that. I'm not going to go there. It's just too much.
And you're all happy about that, trust me.
And honestly, I don't go there because even only time I ever know it is when I'm about to teach a physics class and I frantically cram my lecture notes and go, okay, I got it now. All right, here, let's spout this knowledge because I'm a professor. But I just say that we're seeing an expansion and a cooling, but extremely fast changes in the way the forces interact with each other. And so let's fast forward to 1 second after the Big Bang. Hadrons came about. And hadrons are the protons and the neutrons that form the nucleus of atoms. They weren't atoms yet because they had so much energy that they literally were blown apart into free movement without, there were interactions with each other, but the energy was so much that they couldn't actually stick. It's kind of like, like melting wax or something. The molecules just come apart when they get to a temperature. It's so hot that they won't even form a nucleus, which you can imagine that's much hotter than even the sun. Even the sun has hydrogen. I mean, it's stuck together, there's atoms on the sun. So this is hugely high temperatures. 20 minutes after the Big Bang, nuclei formed for the first time. That's an atom of probably hydrogen, a neutron and a proton that could stick together. Multiple protons could stick together. Only light elements were able to, only light nuclei like helium and hydrogen could form because there was still too much heat. They would fall apart before they could get bigger. And so very strange stuff. 20 minutes after, 20 minutes as nuclei, then nothing happened for 240,000 years.
What?
The universe is characteristic of these times of immense activity, and then nothing really changing for a while, and then more immense activity and nothing changing for a while. And you'll see this in the formation of the universe. So in some ways, I don't know whether to take, I've gone back and forth. At one point I thought, oh, it's got to be 6 literal days of creation because I just think that gives God the most glory. And I thought maybe God uses a nonlinear time scale and he uses Planck's for the first day, and so I don't really know. I don't have a position on this. I don't think it's a salvation issue. Yeah.
But during this whole time, it's expanding.
It's expanding.
So
yes.
for 240,000 years, nothing happens, but it is expanding.
Expanding.
Okay.
And so here's the flatland part. What is it expanding into? And this is the part that my students would have the most trouble with, and I have the most trouble with it. In fact, I started to think about it, and how am I going to tell? Oh, it's expanding into, and I realized I fall into this trap. It's not expanding into anything. It's expanding itself. We are in the space. The universe is expanding into its own. It isn't expanding into anything. It is everything, and it's expanding.
It's making its own way.
That's right. It's as if our universe was like a speck, which then started expanding into a sheet of paper, like flatland. And people are stretching it and stretching it and stretching it in every direction, and it's going out. What's it expanding into? There isn't anything for it to expand into because the universe is itself. It's contained. In other words, the universe is expanding, the space is expanding. It's not that the universe is expanding into space, it's that the space of the universe itself is expanding.
So it's being created simultaneously, if you will.
Yes. It's as if God created this aquarium for us to live in, and then the aquarium just keeps getting bigger. And we ask ourselves, well, what's it expanding into? Well, that presupposes that there's something outside the universe, and whether there is or not, science cannot tell. Because remember, the game of science is I'm going to study the universe, and I'm only going to conclude what I can see, what I can measure. And so I think that's naturalism, right? We get into naturalism, and people who have spiritual beliefs say, oh, scientists are all atheists. Well, maybe some of them are, but sometimes when you play the game of science, you just have to say, if I can't see it, the job of scientists is to study things and study them more and more minutely, or study big things grander and grander, and draw from them the parallels that help us understand the principles of physics. But the universe is not expanding into anything. We are in it, watching it expand. Well, I'll show you how that works. But so the universe is expanding, but it's not expanding into anything. It's like a popcorn that blows up and the parts come out. We'll see that some of the innermost parts of the universe creation are actually on the outer part of it now, if you think about it that way. So let's go back to our 240,000 years, nothing happened. All of the energy in the universe at this point is light. The forces are there, particles can fleetingly interact with each other, but all of the energy is light. And remember that, because we'll come back to that. 150 million years, it's still expanding, still cooling, nothing's happening, and the light is not in the visible particles. At that point, there's very little light of any kind. They call it the dark epoch of our universe. So 200.
Where'd the light go?
Well, it's diffuse, so the light from the original creation is expanding out, but there's no stars yet because nothing's formed. Any real atoms or nuclei are barely formed, but they haven't come together enough to form a star, because a star has to have enough hydrogen get on it that it comes big enough that it becomes able to cause a fusion reaction, which then explodes the star into light. And so no stars yet. So the universe was just dark. They call it the dark epoch. But it's cooled enough that the light of the earlier epochs is starting to dwindle away. The energy is being converted more and more into matter and less of energy.
So the light is converted into matter.
Into matter. And so when I talked last time in the first course about quantum mechanics, we saw that there is nothing in modern physics to prevent matter from disappearing and becoming energy again. And there's nothing to prevent energy from spontaneously becoming matter again. And you could think, oh, maybe we could transport people. Well, it's hard, because the kind of conversion between matter and energy that takes place in our universe apparently happens all the time. It's just very tiny bits of energy and very tiny bits of matter at the current condition of the universe. And so generally today, matter doesn't convert into energy unless you're in a nuclear reactor. But even then, it's a tiny fraction of the mass that's there. But at this point, there was so much energy that there was enough of it to create matter on a wholesale scale. So if you think about it, everything we touch was energy at the moment of the Big Bang. And if you think about it again, like I like to think of it as cooling and like solidifying, like wax. But it's much more complicated than that. It's the energy just became little particles, and the particles became cooler a little bit. They weren't flying around so fast, so they started to have a chance to kind of stick together, and then we formed nuclei, and for a long time they were just nuclei, and then electrons started to get stuck to them, and molecules or atoms began to form. And once atoms began to form, atoms in a neon sign are just atoms in a plasma. They don't do any chemistry because there's too much energy from the neon sign. They just glow with light. But if you turn the neon sign off, then the molecules cool down and they can begin to interact with each other and stick to things. And that's when chemistry happens, and that's when life comes about, or the life that we know of. Biochemistry and that kind of thing requires a cool enough place that the atoms and molecules can interact and stick together and do their dance and all of that. So that's kind of the way the universe is apparently came about. It took 1 billion years after, according to the physicists, I sound like Carl Sagan, 1 billion years after the Big Bang, that was when the first star formed. They would have been a quasar, and it would have been that enough hydrogen started sticking together because of gravity. If you can imagine what kind of gravity, if you had a hydrogen atom, and I drop it, it'll never hit the floor because the currents of heat in the room are enough to just float it around. It'll wind up going somewhere else. But it took 1 billion years for the molecules, or hydrogen nuclei, to begin to stick together in a ball big enough to form something heavy enough that it had gravity enough to crush itself down and light off in its fusion reactor. And you can imagine how big that has to be. So 1 billion years before the first star formed. When the star forms, then what happens is the atoms start sticking together, mostly hydrogen and helium, and they can form other things like lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. All of the elements that we have were formed in stars. And so Carl Sagan, in one of his Cosmos
Star stuff?
talked about, we're all made of stars. Yeah. And what he meant is that everything that we have, all the iron, all the aluminum, everything else, was formed in stars, and those stars blew up and distributed that stuff in space, and later on it came back together and winds up forming a ball of junk, and then that became a planet, or maybe another star. And so if the standard theory is right, then these tremendously creative events, interspersed with long, epochs of nothing, is apparently how everything we have today came to be. And that's what physicists are saying is the process by which the universe was created. So again, I think it's interesting to me that there is a beginning to the universe. The Bible says there's a beginning to the universe. There are these weird creative processes that happen. I don't know about the number of epochs matching up with six days, but it's certainly interesting to me that the Bible talks about creative events in a process and pattern, and that seems to be kind of how things went. So that's the timeline of the universe forming. Pretty weird, huh?
Just the first billion years, though.
That's right, just the first billion years.
So when the first sun, that's when light began, because it's emitting photons. Is that what we're talking about?
The initial light, there's light from the bang itself, because at that point all the energy was just there as a plasma. But photons themselves are particles. So the light we see didn't show up until the the 300. That's the 240,000 years. That's when photons, the particles light is both a particle and a wave, right? That was the last time. Light actually became the only source of energy. That was the predominant source of energy at that point in time.
Now, do scientists hypothesize that there is more than one universe?
No, that's a really good question. Yes, in fact, that goes right into the next. So how in the world do we make sense out of the whole dimensions of the universe? So what? I said the bang didn't happen in space. The bang happened and created the space. So the question about parallel universes really comes down to, if we're in a flatland that's expanding out, or we're living in a number of dimensions, let's say 3 for height, width, and length, and it's expanding, are there other dimensions? Are there another 3 dimensions that we don't know about? Are there another 6 dimensions we don't know about? And you may have heard of string theory. People have been trying to understand why the universe has only 3 dimensions. It's a problem for science because there's lots and lots of ways to explain the universe physics, the grand unification of theories. People want to have a theory that allows the electric field. I'm sorry, Ellen, it's a reflex.
It's the teacher in you.
Normie, I'm just doing hands.
People want to know, the goal of physics is, the physicists are almost religious in their pursuit of simplicity and beauty. They want a single equation that explains electricity, magnetism, gravity, and it's tantalizing how close we are, because the equation for gravity is mass 1 times mass 2 divided by the squared radius, or the squared distance between 2 things, m1, m2 divided by r squared. The same equation holds for electricity. If I take the charge q1, q2 divided by r squared, that equation works for electricity. And it turns out that if I take magnetism, I can use an inverse square law to explain that too. In fact, when Faraday came up with Faraday's law, all he really did was kind of go, wow. I'm not making light of Michael Faraday, who's a brilliant guy, but I'm just saying, he looked at it and goes, well, what if the same equation for gravity, we don't know how that works, but this equation takes care of it. What if I just put the charges in there? Oh my gosh, it works. The only difference is there's a constant. And the constant is much bigger for electricity. That's why it's a strong force. It's much lower for gravity. That's why it's a weak force. And so physics is really just looking for one simple equation that explains all of these fields. And they cannot do it. They cannot do it without having more dimensions in the universe than just 3. And so the question is, how many? How many other dimensions are there? String theory has a lot of fans for lots of reasons. String theory explains everything. It explains, it's pretty close to a unified field theory, if you have enough dimensions. 10 turns out to be really useful. 10, everybody likes 10 dimensions. I kind of like that because we have 10 fingers. But there's a problem. The string theory is based on an idea that time is just another like height, width, and length. But we know time isn't really like, we talk about space-time, but time is different. Leibniz and many other smart people have noticed that, you know what, time, if nothing ever changed, there's no such thing as time. I mean, something's timeless because it doesn't change. And so without change, which requires movement of things in flatland, otherwise there's no clock, I don't know if time's passed or not. It's exactly the same as it was yesterday, and after a while I have nothing to measure. It's like being a prisoner in a cell. You don't know what day it is. After a while you make marks on the cell wall, but if you sleep through one of them, you forget, you start to have no idea what time is anymore. So time depends on the other axes, the height, width, and length. So if you take time and put it in there, you get string theory, if you make it part of the dimensions. The problem is nobody knows if that's the right number of dimensions. If you put in 12, you get a really good model 2, and you can have as many as 30, 40, 50. You can put as many as you want. Kelvin once said, if you give me enough variables, I can fit an elephant, right? Which is basically a way of saying, if you let me put enough variables in an equation, I can make an equation that's going to show your checkbook balance for the last 20 years, and it'll be perfectly accurate. But I may need 40, 50, 60 variables to do it. But that's not science. That's not simplicity. Physicists want the simplest, most beautiful theory that explains everything without being needlessly complicated. It's like Occam's razor. Anything that's more complicated that explains something is less valuable than the simple way of explaining everything. So left to themselves, physics tries to make things simple. String theory makes things complicated. And it leads to parallel universes. It leads to the possibility of time travel. It leads to the possibility of wormholes where you can pop in and out of things and go from one place to another. And physicists are just like us. They want those things to be real. We do, don't we? I mean, if I told you you can never go back in time, you can never travel faster than the speed of light, I'd be really disappointed. And there's a great book called The Physics of the Impossible. If you want to read an interesting book, it's all about how these impossible things might be possible, and if physics is just a little wrong, or we have enough dimensions in string theory. So yes, parallel universes, there are physicists who will go to the math, there's parallel universes. Another reason why there's people that want string theory and parallel universes is it looks like, and I hope I have time to get to it, it looks like this universe is very unusual. If it had been even a slight bit different how the Big Bang played out, there wouldn't be any chemistry, there wouldn't be any heavy elements, and there wouldn't be any way we could have the diversity of chemistry needed to make life as we know it, living things. And so the physicists don't like the idea that the creation has to be so perfectly engineered to create life. And because it just seems like there's a God. And it almost seems like they feel like they're fudging their math to allow us to exist. And that's repulsive to the game of looking at the creation completely objectively with no spiritual compass to guide your interpretation of the data. So the game of science kind of prohibits that. And so that's not done. But so you see there's lots of reasons why parallel universes are useful, because if there's a million or billions of parallel universes, we just happen to be living in the one where life happened. And so that's the game that parallel universes makes it possible to explain life. And so that's kind of the paradigm people have. Turns out you need way more than 1 billion universes to possibly get the odds to work in favor of there being one. So that's, for me, I don't see that. I tend to think, okay, whatever. I'm not gonna disallow God and make the math more complicated just to not have to have a God.
What I find interesting about that, I like to listen to science programs, but I mean, there's an element of teachers and scientists, right, that are atheists, and what I always find interesting is that it's another element of faith. You've just chosen a different faith,
Yes.
right? Because since you'll never know in 1,000 lifetimes probably these answers because of how big
That's right.
everything is. If there's parallel universes, if there's 1 billion, or how life started, It's all faith.
It is.
It's just a science faith, atheistic faith.
That's right.
That's where you've taken to go, versus where we've accepted, right, that there's a God that created everything. It's just a different faith, because they'll never know. It's all, the math is good for today, and in 10 years someone else is going to come up with another
That's right.
mathematical variable that will be better than the last one, but still doesn't explain. Because that's what I've noticed science do, is that they come up with a new, right,
Yes.
concept, and then they build on it, they build on it, they build on it, but they never truly know.
No, and we'll see there's some huge blind spots where we've missed things. We're just recently discovering things that we've totally gotten wrong. So let's say string theory. Some theories go as high as 26 dimensions. There's an interesting paper that mathematicians look at dimensionality much different than we do. We think there's 3 dimensions, 4 dimensions, 5 dimensions. Those are axes on a graph, so I plot it. There's this thing called fractional dimensions, and mathematics can arrange to be 2.5 dimensions. And there's a paper in Nature that came out in the last 5 or 6 years that said there's 2.78, the number, if you're a math geek, 2.7.
Did they round up?
2.7. No, it's a transcendental number, it goes forever, 2.1.
Oh, it's like pi?
Something.
It's in a round.
Yeah, that's how many dimensions there are. And that turns out to maximize the amount of information in the creative. It gives the universe the greatest amount of possibilities as far as creating different things.
Oh.
So, people have, it's just crazy. So the question is, why don't we see these other dimensions? It certainly seems like there's more than 3. And that's why flatline is so relevant. Most physicists believe that there's at least 4. And I can give you a good argument for the 4th dimension here pretty quick. But the idea that we don't see these other dimensions, why don't we see them? Well, we actually kind of do. There's some ways that we can get a hint that there's more dimensions. But the other reason is that physicists think that it's possible that the flatland universe we're in, I'm going to go back to imagining we're flatlanders, that it's folded. And it's folded in such a way that it's so thin, because remember, it's infinitely thin, that it's just like a origami, but it's all folded up. So we don't see the other dimensions because they're infinitely close to us. There's no, they're so small that they're smaller than an atom. In other words, there's a 4th dimension, but it's smaller than an atom, and nobody can see it.
Couldn't it be possible to see it as a shadow? That is, if you're in flatland and there's somebody in another dimension above you,
Yes.
I would suspect you could see it as a shadow, so to speak.
Yes.
As some form.
And gravity is the shadow.
Okay.
We actually gravity is this weird thing. Nobody's understood gravity. You remember the gravity waves and the graviton, the discovery of graviton. If you're not a really, cosmos geek, I'll tell you that gravity is the one that actually, that shows us a 4th dimension, I think. So, okay, so let's go back to expansion for a second. Now let's talk about more modern times, not 300 million years ago or whatever. But Hubble was an astronomer, and Hubble was one of the Hubble Space Telescope, named after Hubble, was able to, and Hubble himself actually, before the Hubble Space Telescope, took a picture through a telescope that changed our whole view of the universe. And it was that, if you remember the picture that has all these little stars in it, and if you zoom in on one of the stars, each one of them is a little galaxy, a little spiral galaxy. We live in the Milky Way galaxy, which is kind of a spiral collection of stars. And we're not anywhere near the center because that's a dangerous place. There's cosmic rays and living things die there. So we're kind of at the edge of this universe, this little Milky Way galaxy. And Hubble looked into a place where there were no stars, particularly in the sky, and at great magnification, he saw more stars, kind of dim ones. And the optics got good enough that they could take a picture of them and see that they weren't stars, they were spiral galaxies, just like ours. And that's when people realized for the first time, there's about 10 to the 11th stars in the sky, or 10 to the 11th stars in our galaxy. There's about 10 to the 11th galaxies in the universe, according to the Hubble's estimate. These are all just estimates. In other words, it was a huge thing because physicists could say, we're not special, we're not the center of the universe. Get off your high horse, human beings, because we're just one of 10 to the 11th galaxies, and we're one of a minor planet. So that's when people began to think there's life everywhere in the universe, because if there's life in the Milky Way, how much more so if there's 10 to the 11th other chances to roll the dice and create a living, livable planet? There must be life out there. And so that was a huge change to realize that the number of inhabitable worlds might be huge in the universe. So the Hubble, one of the biggest discoveries Hubble made, changed the way we think about our universe. The other discovery that Hubble made was he discovered that the light coming from these other galaxies and stars was not quite the same color as the light we see in the laboratory when we heat up a piece of iron and measure the light coming from it. Really heat it up like white hot, and you can measure the atomic emission lines coming from the iron. It's a geeky thing to do, but people do it. It's still just looking at creation, looking and studying creation. It turns out that if you look at the stars far out in space, you see iron. And we know that there's iron in that star, that star has some hot iron atoms in it. And so we know very, very well, shockingly well, what the elemental composition of stars is. We can tell you if a star has zinc, iron, magnesium, so we can measure sodium really, really well. So we know that the chemistry and the atoms of the materials that we have here in our galaxy exist in the other galaxies. So that's an incredible discovery if you think about it. We have the same chemistry everywhere in the universe, apparently, which I would, it's not a given. And so, but they're slightly different. The farther the galaxy is away, those lines move a little bit to lower energy. And Hubble found that the further away the galaxy is, the more they're moved to the red. And he actually measured the ratio of distance to shift and calls it the Hubble constant. And what they realized it's caused by is just like when the ambulance goes by your house and the siren goes, it goes by. We have a car, we have a motorcycle that goes by, drives us crazy. But it's always, the sound goes down like that. Light, when its wavelength drops, it shifts towards the red. So what Hubble discovered is that all of the galaxies are moving away from us. All of them. They're all moving away, and the farther they are away, the faster they're moving away from us, which is a very puzzling thing. It makes it seem like we're the center of the universe. Literally, my eye, everything's expanding away from us.
So you're saying they're accelerating?
Yes.
Faster.
Well, that was a more recent discovery, but Hubble just knew that they are moving away. And the things that are the furthest away are moving away from us the fastest, which is a very puzzling thing. Until you think about flat Earth. If you're on that sheet of paper and we stretch it between us and we start stretching that sheet of paper back and back and back, two places on the sheet that are very close together will come apart a little bit because there's going to be some stretching. But if you put a mark here and a mark there instead of like close together, there's more rubber in the sheet between the two far apart objects to stretch. And because of that, whatever is furthest apart moves away from everything else at a higher speed at the same stretching. Can you follow me? It's like a flexible sheet. So if I blow up a balloon and I put 2 points on the balloon, as I blow it up, those points are going to get further apart as the balloon stretches. If I make the initial points further apart, they're going to get further apart faster as I blow up the balloon. So what Hubble discovered was that our universe is expanding, and they can measure the rate at which it's expanding by how much shift. And the universe, anywhere in the universe that you happen to be, you're going to see everything else moving away from you at a speed that increases the further away it is. And so the expansion of the universe was just visually was confirmed in 1929. That was when this was discovered. So our universe is expanding. It is like flatland, and it is flexible. Our universe is stretchable. It's a stretchable thing. Our universe is three-dimensional, so we can't imagine stretching in 3 dimensions, just like the flatlanders can't really imagine their universe stretching either. But it's stretching. And
is it really stretching if it's not expanding into anything?
it's yeah, that's a good question. Space, they call it spatial expansion, but it's not yet. It is not expanding into anything. It's just that the fabric of space and time is getting spread out more over time. Isn't that bizarre? So
Yeah, because then that's the problem, right?
yeah, it is. I tell you, this is it's mind bending. So now, we also know that when we look into the night sky, what we're seeing is light that's coming to us from far away. and it could be thousands of light years away, which means that the light you're seeing from a star that's 1,000 light years away, it's 1,000-year-old light. So when you look at that star, the light is very, very old. The star could be long gone. It could have exploded and not even be there anymore, but you're still seeing the light. I think if the sun suddenly turned off, I think it takes 30 seconds. Somebody may know, 3 minutes, 30
I
seconds.
thought it was 9 minutes.
Maybe it's that. Yeah, we wouldn't know right away because the sunlight would still keep coming at us, and then after 9 minutes or whatever time is, we go, hey, the sun just went out. What's going on? But we wouldn't know because what we're seeing, everything, all the light we see that we do our observations and science with, is old light. And so not only is the light shifted from these stars, but it's old. It's ancient. And so as you look out into the night sky further and further, you're looking back in time. Not because time is part of the universe, but because the way we perceive light, which is the only thing we can see about the universe, that our perception of it is changed because the light is coming toward us and takes a long time to get here. So light when we look into the night sky, the universe does exist out there and it has a presence, but we only see the past as we look out into the sky. So, this is a crazy story. In 1956, there were two young scientists named Penzaz and Wilson, and they worked for Bell Labs, and they were setting up a microwave receiver to try to receive microwaves to do communication, because Bell Labs is all about communication. And they had this pesky background signal that they couldn't get. They pointed away from it. Everybody turn off all their transmitters, and they point this thing up at the sky, somewhere that there's nothing, and they would get this background signal. And they're like, gosh, it's crazy. So they're checking the lights in the men's restroom, everything else, trying to figure out what's causing this noise, because they got to get it quiet so they can make this measurement. And so they point the antenna in a different way. They're trying to find where it's coming from, and it turns out every time they're pointing up at the sky, they see it, and they can see it over here, they can see it over there. So they assumed it was a problem in their instrument. It wasn't. And somebody else confirmed this background at a different place in Australia or somewhere. And it turns out that they were measuring something called the cosmic ray background. They were seeing it especially when they looked where there's no stars. There's just empty space, and there's not very many places in our night sky where you can do that, because our Milky Way is a flat band. You have to look out of the Milky Way, away from the Milky Way, and then in a place where there's no stars. And this same exact microwave signal is coming from everywhere between the stars and the night sky. Those two young scientists who were trying to set up a microwave communications link, it's like two cable guys. They got the Nobel Prize in physics because it turns out that if you take the energy from that 300 million years of light, that right after the Big Bang, that bunch of light, the epoch where everything was light, that light is very far away, and it's very redshifted because it's so old, it's so far away. It's redshifted all the way down from light down into, light is a continuum. So it's not light, it's not radio, it's microwave. It went from almost UV, it went through the visible spectrum, infrared, all the way down to microwave. That microwave, they were actually looking at light from the Big Bang. And that's why we really are pretty sure there was a Big Bang. We can actually observe it. And because the Big Bang happened in one spot and the universe expanded, that one spot is the light that was released at that time is coming back to us from very far away, but it's the same in every direction because the universe was the same in every direction at that moment. So to me, that was just like, you gotta be kidding me. So we really can see some of the energy released at that original Big Bang. Well, not exactly at the beginning, but like 300 million years after the Big Bang, when the light became visible. So God said, let there be light, and literally it was created.
You use the word light all the time. Is that like our visible light coming from the sun? Is there like
Yes.
Shortwave infrared? Is there like ultraviolet? Or
There's a whole spectrum of it. Yeah, exactly.
Okay, there's a whole range of wavelengths.
It is. When I'm talking about light, I'm kind of meaning all electromagnetic radiation from cosmic rays all the way down to just heat and infrared. And as the redshift happens, what was high energy UV light, which give you a sunburn, moves down and down and down until it's just this weak little microwave signal that wasn't seen until these two kids in 1958 caught it on an antenna. So you never know when you're going to observe something that gets you a Nobel Prize in physics. So be observant. So anyway, so everyone sees themselves kind of at the center of this expanding universe, because we're a spot on an expanding sheet of paper, and that everything's expanding away from us because we're at our particular spot. And so the question is, okay, let's imagine what's going to happen to our universe. We're in an epoch where matter is mostly stable. We have chemistry. Things are expanding away. Things are getting cool. Is the universe just going to keep on expanding, or is it going to stop, or is it going to go back together and have a big crunch? And so people are asking the question: is there a big crunch, or does it just keep going forever? What's going to happen to the universe? And when I was in school, everybody thought, oh, it's just going to, it's just going to keep expanding. Everything's going to get really cold, and there won't be any more energy, and it's just going to have this heat death thing. The universe just becomes, nothing again. But it turns out that the critical mass of the universe, how much mass you have depends. So if the universe has a lot of mass, then it's going to eventually start being attracted together by gravity again, and all the process is going to play out backwards, except stuff is going to crash into the middle of the universe, and then we're going to have crunch. So you got a big bang, and then it gets attracted back by gravity and has a big crunch. If the matter of the universe is not enough, that the gravity is not very strong in the universe, then the thing is not going to overcome the expansion, and it's just going to keep going forever. So the big question up in my lifetime was kind of what's going to happen to the universe.
What's driving the expansion? It's called. I mean, I can see how gravity's pulling it together.
That's a really good
What's
question.
driving?
That turns out to be another Nobel Prize question.
Why did you figure that out?
I mean, people originally thought it was the energy from the Big Bang, this huge, massive amount of energy, and at the end of it, it's just continuing to expand outward. There's no force to turn it around. In physics, there's nothing everything's going to move in a straight direction until some force acts on it. And so the momentum imparted when the Big Bang happened started everything moving away. And the question is there enough force to turn the train around, or is it just going to keep going? And so the Big Bang is the motive force for the expansion, as up until about year 2000. Then we got another answer. So I'm going to try to get all the way to modern physics in 10 minutes. Let's see if I can do this. So the critical mass of the universe turns out to be about 5 atoms per cubic meter on average. If the whole universe has 5 atoms per cubic meter, which is almost nothing. It's just almost no material at all.
Really.
But you're averaging across the whole universe. So, and the regions in space where there's nothing, there's really almost nothing. So if we are above that 5 atoms per cubic meter, then there's going to be a big crunch. And if we're below that, then there's going to be a forever expansion. And so
We're at 4.5.
The best estimates we have of the matter we can see is 0.2. So people say, we're an expansion universe, and up until less than 10 years ago, that was the view. It's okay, we don't have enough matter, so we're just going to keep expanding. It doesn't really matter. It's just going to happen in our lifetime.
Yeah.
Right. So nobody really cares. Okay, but that's the grand answer, right? Is it going to keep expanding? So, but in 1998, they made this huge discovery. There was a supernova in 1998, and people measured the light from it, and they knew where it was because there had been another supernova nearby, and they had figured all this out from the redshifts. Well, it turns out that this supernova was way farther away than they thought it was. It shouldn't have been anywhere near that far away, and the only explanation is that somehow the rate of expansion is increasing. It's the opposite. It's not even just expanding forever. It's actually going faster. So I think you made the point that is that constant rate? The rate of expansion is not constant, and it's increasing. And that was
But that means a force is acting on it.
a force is acting on it. Very good physics. Hey, I spent a long time with my students trying to, if something's accelerating, there's a force acting on it. If the universe is accelerating in its expansion, what is the force? What could possibly be the force? And it turns out in 2013, they set a satellite up called the Planck satellite to measure that microwave background. And they measured it again, and they got a very, very, very careful measurements of the microwave background. And out of some math that I won't go into, they came up with the idea that there must be something in the universe that's making it expand faster than the matter we see. And they came up with the idea that there must be something like only 5% of the matter in the universe is what we see. There's another 27% of the energy of the Big Bang that's in some other matter that we can't see. And not only that, but that matter has its energy associated, which is 68%. That's the current estimate. 68% of all the creation energy, all the Big Bang energy, is in some form that we can't measure. And somehow that energy, not only does it exist, but it exists in like an anti-gravity mode where it pushes things apart. And I didn't even get
Is
into
that what they're calling dark matter?
dark matter. Dark matter. And so if you've heard about dark matter, it has literally only been just postulated because nobody has measured it, no one has seen it. We just are seeing its effects. And dark matter appears to be causing the universe to increase. Not only that, but apparently space, the nature of our universe, creates dark matter. So as it expands, it's creating more dark matter, which is causing more expansion. Nobody has a clue what it is.
Well, when you say create, they don't literally mean create, right? I mean, because my understanding is whatever existed already, I mean, as far as what we call the mass,
Yes.
already existed and it's just changed form.
That's right. They're saying that because it's causing, they believe it's like an anti-gravitational effect. So they're using the same rule of, if the two masses divided by r squared and the two q's divided by r squared, this thing that is accelerating the universe, it must obey the gravity rule. It just has a sign change on it. And so they believe, it's got to be matter because only matter causes gravity. So the dark matter is what they think is causing this acceleration. And the dark matter must be coming from dark energy by the equals mc squared law.
If there were multiple universes though, and they're all expanding, right, we're our own individual,
Yeah.
then it might seem that the other universes which have mass might pull you.
That's interesting. Because we know, so I didn't get into it, but Einstein's general relativity is gravity is caused by a curvature back to flatland. Imagine yourself as a flatlander and you put a marble on the paper. It's going to cause a little dimple in the stretchy universe, and things are going to want to roll down into that hole. So if you're it's like the miniature golf green where you put the ball and it rolls and tries to go down the little hole. So Einstein's general relativity, formed a classical theory of gravity that is based on the curvature of our three-dimensional space, which we can't envision. They talk about curving the universe. They mean like you're a flatlander and there's a curve in the plane of paper. But we're 3 dimensions and that's curved because there's a 4th dimension. That's why everybody believes there's at least a 4th dimension because of
I've always seen that as a single plane, like when
Yes.
they put a little rubber ball or something. But wouldn't that be in multiple planes, really, across all axes?
Yes,
Right.
exactly. What they're saying when they show you that flat table
Right.
with the dimple.
We're really talking about all the way this way, all the way that way.
Yeah, that's the part that is hard to get across to
Right.
students and stuff, is that they're talking, the plane with the dimple is a flatland representation of our 3-dimensional universe, where they've just thrown away 1 dimension because we can't think about it, we don't know how to do
Okay.
it.
So they express it only in 1 dimension, but it is it's all the way around.
When they write the equations, there's 4 dimensions.
Okay.
But we can't draw a picture of it because that you can't plot in 4 dimensions yet. I don't know how to do it. But,
Next week.
next one. So dark matter has this effect of causing us basically to have to start over to try to understand what's going on with the universe. We do not know what dark matter is. It seems that we only measure 5% of the energy in the universe. All the sunlight, all the energy that we see around us, all the energy that's been converted into planets and people and plants and everything else, that's apparently only 5% of the actual energy released at the creation event, or the Big Bang, or the singularity, if you want to call it that. And only 5% of the matter, the stuff we're seeing here, it's only 5% of the actual matter in the universe. The rest of it's dark matter. Only 30% of the energy of the big creation is energy that we can see and feel and measure and know about as scientists. So right now, and we're going to watch this all unfold, who knows what dark matter actually is. And isn't it interesting that people, after all this time, it's all turned upside down again? We're living in an incredible time of discovery. It's very, does this matter? No, I still have to go to the grocery store. I still have to go to the grocery store.
May the
but-
force be with you.
Yeah.
It's just amazing this is what attracts people to science, is looking at creation carefully uncovers such strange, unbelievable aspects of things that that it's like a crossword puzzle, I think. For scientists, it's kind of just a puzzle. It's fun to figure it out. It doesn't change our lives, but the idea that there's this whole new thing we have to understand, it's kind of exciting. It's like, wow, again, I thought we were getting near the end of the puzzle when Newton wrote down his gravitational formula.
Well, it keeps us humble and keeps us searching. You know, it's
It
like
does.
if all the answers were already out there, then.
Wouldn't it be boring?
Yeah, very
Wouldn't it be
boring.
boring?
And also, you know, we are a faith-based group, so it leaves room for those bigger questions. So.
And I think God lets us see under the hood. You know, it's I don't think He expects us to become wise from it, but I think He indulges our curiosity. And how would we figure out, how would we find 4 dimensions? I mean, that's incredible to have any evidence for that at all. And by the way, there's a great picture from that. It's a Keller telescope where actually they looked at stars right by a black hole. And the picture of the stars is warped by the curvature of the universe.
Wow.
So you can actually go out and look. If you look for the Keller telescope warping space-time, you'll even get that picture, and you can see these nice little spiral galaxies. But the one that's near where the black hole, which you can't see the black hole because it's not light, it doesn't have any light coming out. But the galaxy looks kind of warped, like it's like a little mushroom, like you had a bad camera, you dropped your camera and it's not taking clear pictures. So this stuff is, the more we build instruments and the more we make measurements, the more we find out that, wow, we really didn't know much at all in the beginning. So stay tuned. By the way, funny story, Albert Einstein, when he wrote the general relativity theory, he included something called a cosmological constant. And it was a tiny little number that he had to make to get the universe to work out right. And the number was like 10 to the minus 122. And if you didn't have that number, his theory failed. And he got slammed for putting this fudge factor into his theory, because some physicists like, where did that number come from? It's almost zero. It should just be, that's wrong. And Einstein knew he didn't like it either, and so he called it the biggest blunder of his career in his later days. He said that was the biggest blunder ever. Turns out the dark matter, it reintroduces that number. So Einstein wasn't necessarily that wrong. He knew there was something bogus, and he didn't. Who would have thought? You know, who would have thought? It would make a whole new kind of matter. He really would have gotten bad critical reviews if he said that. But, so, will we have time travel? Will we have wormholes? Will we be able to go faster than the speed of light? I sure hope so, but the jury's out.
And maybe not in our lifetime.
Maybe
Probably
not.
But it makes for good science fiction.
Yes.
Well, I really do want to go visit my young self again.
I know.
Are you saying that the dark matter is similar to taking a pencil and sticking it through the paper for the Flatlanders? Ish?
It certainly could be.
In the sense of that they wouldn't know that was another dimension?
It seems to me that if our intuition about pencils and papers and curving and folding and things is right and meaningful in any way, which it might not be because we're finite, then maybe these weird things that we're seeing are caused by something that's very simple, that is explained by our intuition, but we just don't have the right dimensions or the right
words.
pictures, the right words, yeah. And see, again, physicists love that idea that there was a paper I just read in Nature where they said, well, this is a good theory, but it doesn't agree so much with intuition. And I went, wait a minute now, intuition, this is science, where does intuition come in? But people want the universe to fit their intuitive, rational mind. And the rational mind seems to have come a long way in understanding the universe. So did he craft our thinking and give us mathematics to be able to unravel some of these things? And, I don't know, I can't balance my checkbook, that's why you do it, so.
Have they explored, I imagine, have they explored the possibility that the dark matter is like, for lack of better words, hydrogen atoms that just haven't coalesced, like into a galaxy or a universe or a sun? I mean, because the galaxy or the universe is so big, you know, the hydrogen atom might not, it doesn't have much weight, but if you spread it out through everything, it probably makes a difference.
That's interesting.
So would it come up as a different wavelength or something?
Well, it would just be floating in a vacuum, right? It would
Yeah.
just be some hydrogen atoms that are out there that just haven't formed into a sun. But
Right.
if you have this big old lake of nothingness, maybe there's enough hydrogen atoms in there to account for that. I don't know, I'm curious,
No,
I'm
I don't
asking.
I talked to a physicist just a couple of weeks ago who told me, I didn't know this, but there's an anti-hydrogen, there's antimatter, there's an anti-electron, there's an anti-proton. But apparently they can make anti-hydrogen, which is, it's antimatter. But I don't know if antimatter has an inverse gravitational, does it have an anti-mass? And I don't know if there, I just don't know. I'm not.
I know that came out in the Star Trek series.
Yeah.
Was antimatter a
Very
thing
Star Trek.
before that?
I think they always thought it was like theoretically possible.
Okay.
But because there is a positron and an electron, which we knew about from old, the 1950s. And the positron is an electron that's positively charged, that's wrong. If your college students are like, the electrons always have a negative charge, but there is a positron, and it can be released in some radioactive decays. But I guess, and there's apparently an anti-proton and an anti-neutron. So you can apparently make chemistry with antimatter, but that's just
They have a mass then.
They do,
Okay.
and that's where I believe their mass. The textbooks I've been taught from say the mass is exactly the same.
So it's
the same
identical.
mass, but
Okay.
so it's not a negative mass. But negative mass is kind of a weird. Whatever this thing is, if Einstein's gravitational theory is right, it's instead of causing a dimple, it's causing a upward. Whatever this dark matter is, it's causing the space-time to go.
Well, the negative doesn't relate to mass; it relates to its charge. No.
Well, for gravity, there's no charge involved. It's that would be the electric force if there was a charge. Gravity's apparently just related to mass.
Right. Right.
Yeah. So, but anti-mass. If it were anti-gravity causing this acceleration, then it would have to be anti-mass. I don't. That's science fiction to me, as far as I know. But when I say science fiction, I mean it's probably true, but we just don't know it yet.
Keep working on it, Tony.
Yeah.
Oh no! I love watching the science
But Tony,
programs.
that's exactly how people get Nobel Prizes. It's just that kind of like, no, this got to make sense, and they make some crazy idea like who would have thought time was faster for people that are moving than it is for people that are standing still, and yet we do it. That's known every day. Your GPS wouldn't work without that calculation. So very odd.